This is the first 6.3 video. We're going to look at binomial random variables. And the first objective is to determine whether the conditions for a binomial setting are met. So a binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. There's four conditions for a binomial setting. First is binary, where the outcomes of each trial have to be able to be classified as a success or as a failure. Trials have to be independent. So knowing the result of the first trial can't tell us anything about the results of any other trials. They don't influence each other. Third, there has to be a set number of trials in advance, and then it has to have the same probability of a success for each trial. So let's look at a couple of examples and determine if the conditions are met for a binomial setting. So the first scenario, genetics say that children receive genes from each of their parents independently. Each child of a particular set of parents has a probability of 0.25 for having type O blood type. Suppose these parents have 5 children, and let's say X, the random variable X, is the number of children with type O blood. So is this a binomial setting? Now, the trick for determining if a random variable is binomial is check your bins. Binary, independent, number, same probability, stands for bins. It's just a way to remember the four conditions for a binomial setting. So let's apply bins to this scenario. In this situation, the outcome is binary because they're either going to be type O blood, a success, or not type O blood, which would be a failure in this case. Are trials independent? Well, they tell us that children receive genes from each parent independently. So no matter what the blood type of the first child is, it doesn't influence the blood type of the next child. So yes, the independent condition is met. N, is there a set number of trials? In this case, they told us, suppose the parents have 5 children. So there is a set number. Of the 5 children, X represents the number of children with type O blood. So N is met, and S, the same probability. Since the trials are independent, the probability of each success or having type O blood type is 0.25, like they've said. So like I've said, each of the conditions is met. They are binary. Child blood type is independent. There's a set number of trials because they told us there are 5 children. And the probability of success, which you can see here, P equals 0.25, is the symbol used for the probability of a success, and it's the same for each child. Let's look at the next scenario where we shuffle a deck of cards. We flip over the first 10 cards one at a time, and Y represents the random variable, the number of aces you observe. So in this case, we're going to use bins again, and B, is it binary? Yes, it's either an ace or it is not an ace, a success and a failure. Are trials independent? In this case, the trials aren't independent because if I flip over that first card, then, and it is an ace, then the probability of the next card being an ace changes. So the outcome of the first card influences the probability of the next card being an ace or not being an ace. Then we can rule out right there that it's not a binomial setting just because of that. So again, for this case, it is binary, but it is not independent, which means it is not a binomial setting. There is a set number of trials, and the probability of success is 4, because there's 4 aces out of 52 cards, so 4 50-seconds. But again, it's not the same for each trial, so this is not a binomial setting. You could make this a binomial setting if you just replace the card. So when you flip the first card over and see if it's an ace, if you put the card back in the deck and then shuffle them, and then draw the next card, then the probabilities of the cards being aces are independent. No matter what the first card is, he still has a 4 out of 52 chance if you're replacing it and shuffling again. Let's look at our third scenario here where we shuffle a deck of cards and then we turn over the top card. We put the card back in the deck and shuffle again. Repeat this process until you get an ace, where W, the random variable, is the number of cards required. So this is similar to the scenario I just said, but it's a little bit different. And let's run through and check bins to see if this is a binomial setting. So the outcomes, as you can see, are binary. Ace is a success, non-ace is a failure. The trials are actually independent because we are replacing and reshuffling the cards. So there's still a 4/52 chance of an ace. But in this case, there is no set number of trials. W is the number of cards it requires to get the first ace. So we don't know how many trials it's going to take. We're going to keep going until we get the first ace. So in this case, it is not binomial because there's no set number of trials, even though the probability of success is the same for each trial. So this is actually an example of a geometric random variable, which we're going to learn about in a couple of videos from here.